Why can a truck brake using its own engine and at the same time produce a sound so deep that it can be heard hundreds of meters away? This question arises every time a heavy vehicle descends a slope and the air fills with a deep, sustained roar that has nothing to do with conventional brakes. It is a sound that stands out above traffic and that many interpret as a sign of wear or an unnecessary noise, although its origin is completely different from what one might think at first glance. On a mountain highway or on a straight road with a slight slope, a truck in full descent activates an internal system that temporarily modifies the engine's behavior. It does not seek to propel it or increase its power. It does exactly the opposite. The engine stops pushing and begins to offer resistance, becoming a tool to control the vehicle's speed. That deep sound heard during descent is not a defect. It is the audible signal of a mechanical process that allows maintaining control without overloading the main brakes. This system is known as an engine brake or Jake brake, and its function is neither decorative nor secondary, since it is part of the set of mechanisms that allow a truck to moderate its speed under demanding conditions without relying solely on friction. The reason is simple. The energy that a large vehicle must manage while moving is so high that a single system is not enough to guarantee safe and consistent braking over kilometers of descent. For this reason, the engine brake acts from the very heart of the vehicle and responds to a specific need that arises when mass, gravity, and inertia work together. That need explains why trucks cannot rely solely on their service brakes. In this context, the presence of an auxiliary brake ceases to be a technical detail and becomes an essential part of vehicle control. Understanding why it exists requires looking more closely at the problem it seeks to solve. What makes a truck require an auxiliary brake to control its speed without relying only on its main system? The need for an auxiliary brake appears when one considers the enormous amount of energy that a heavy vehicle must dissipate every time it reduces speed. It is not a minor detail or an optional solution. This becomes clear when considering that a moving truck accumulates an amount of energy that easily exceeds what the service brakes can handle when braking is maintained for minutes. That energy does not disappear on its own. It must be transformed and dissipated in a controlled way. Here, the problem begins for any system that relies solely on friction. In this scenario, when a truck is moving, its mass generates energy that increases with speed. And even without using numbers or formulas, it is enough to understand that a loaded truck moves tens of tons. Braking that weight every few seconds requires converting all that energy into heat. In specific situations, such as stopping at a traffic light or adjusting speed on a gentle curve, the service brakes work without complication since they are designed for that. But when the vehicle faces a long descent, the scenario changes completely. On a constant slope, gravity drives the truck downward continuously, and the driver must oppose that movement to keep the speed under control. If relying only on the service brake, every second would involve applying friction, and that friction generates heat, which, as long as the truck continues descending, accumulates inevitably. Over time, the drums or discs heat up beyond what they can withstand, and the friction material loses effectiveness as it reaches high temperatures. This progressive loss is known as fade and consists of a reduction in braking capacity caused exclusively by heat. When fade appears, the driver must apply more pressure to the pedal to achieve the same effect, and in extreme cases, the brake almost stops responding. It is not a mechanical failure, but a physical limitation of the system because friction cannot remove energy indefinitely without degrading. The accumulated heat eventually exceeds the point at which the material retains its properties, which is why prolonged descents represent such a great challenge for trucks. Under these conditions, the vehicle's mass acts constantly. The slope adds a push that does not stop, and time prolongs the effort, so that the combination exceeds the safe margin of a conventional brake. If a truck were to rely solely on its service brakes during a long descent, the internal temperature of the drums or discs would rise until their effectiveness was completely compromised. In this context, the auxiliary brake exists to solve this problem, and its function is not to replace the service brake, but to assume most of the load in situations where heat could become a risk. An auxiliary system can operate for minutes without degrading, because it does not depend on friction nor generate extreme heat in critical components, allowing the truck to regulate its speed without constantly resorting to the main brake. This distribution of work keeps the system within safe limits and extends its lifespan. For this reason, the need for an auxiliary brake is not optional on mountain routes, highways with long inclines, or long-distance heavy transport, where it is as indispensable as the service brake itself. Its presence ensures that the truck can descend without loss of effectiveness and without the risk of fade, and it also preserves the capacity of the main brake for specific situations that require more immediate braking. Instead of relying solely on brake friction, this system uses the engine itself to generate resistance and control the vehicle's motion. What allows this effect is not in the wheels or transmission, but in a process that occurs inside the engine itself, when compression stops working to drive motion and begins to oppose it. For an engine to act as a brake, it is necessary to alter the way compression behaves inside the cylinders, because under normal conditions the pressure generated during the operating cycle contributes to pushing the piston and producing motion, whereas when using the engine to hold the vehicle, that same compression stops being used to propel and becomes resistance. When the engine brake is engaged, that logic is modified and the energy that would normally be transformed into propulsion is released in a controlled way, so that the piston no longer receives the force characteristic of normal operation. Instead of delivering power, the engine begins to absorb part of the energy coming from the wheels. This effect is achieved through a system known as the Jake brake, which acts directly on the exhaust valves, where the key to the braking effect is found. The fundamental concept is simple, because instead of allowing the pressure accumulated in the cylinder to drive the piston, the valve opens at a very precise moment and releases that compressed air, so that the immediate consequence is that the piston receives no power and its movement becomes an effort that opposes the engine's motion and, by extension, the truck's. To understand the principle more clearly, it is enough to observe the basic engine cycle where the piston rises and compresses the air inside the cylinder. And under normal operation, this compression represents stored energy ready to push back the piston during the next phase. With the engine brake activated, this energy is not recovered because the exhaust valve opens just when the pressure reaches its maximum point and the compressed air is released before it can push the piston. Losing that thrust, the piston must continue its travel powered only by the engine's inertia, which in this mode acts as resistance. In this way, very effective retention is generated because the piston's effort no longer translates into power that drives the vehicle but becomes a force opposing motion. The crankshaft encounters constant opposition, and that opposition is transmitted to the wheels through the transmission, so that the engine brake acts without the need for shoes or discs to make contact without relying on external friction, since all the action takes place inside the engine in the relationship between piston, valve, and air compression. Under these conditions, the system's effectiveness increases the greater the vehicle's mass, because a heavier truck generates more energy that can be absorbed by the engine brake without degrading, and this occurs without producing the kind of heat that would raise the temperature in the service brakes, since the energy is dissipated through the engine itself and its cooling system. In this way, it can work for kilometers, absorbing load without losing effectiveness, maintaining continuous resistance on long descents that allows controlling speed without constantly relying on the main brake. This same operating principle prevents the truck from gaining excessive speed on long slopes, because the constant compression of the air and its release at the appropriate moment produce a stable mechanical braking effect in which the engine absorbs energy every time the piston rises, allowing the transmission to operate within safe limits and the speed to remain stable without the need to use the main brakes. This stability is what makes the Jake brake an indispensable system on mountain routes and on journeys with significant inclines. Even so, the effect of the engine brake does not depend solely on compression, but also on what occurs at the exact moment when the air accumulated inside the cylinder is released. It is at that moment when the engine's operation changes completely, and when the phenomenon occurs that not only allows resistance to be generated, but also produces the deep, characteristic sound that accompanies trucks on long descents. At that instant, the phenomenon that defines the operation of the engine brake occurs, a moment in which the pressure accumulated inside the cylinder is released suddenly, and the engine stops propelling to begin opposing motion. This release not only generates the retention that keeps the speed under control, but also the deep, characteristic sound that accompanies trucks on long descents. What happens inside the engine so that this release of air produces such an intense and recognizable noise? When the engine brake engages, the pressure accumulated inside the cylinders is released abruptly at the point of maximum compression. And that sudden escape of air is the source of the deep sound that characterizes this system, since each time the mechanism acts, the exhaust valve opens precisely when the pressure reaches its highest point. Instead of using that energy to drive the piston, the air is expelled suddenly into the exhaust manifold, generating a high-speed flow that produces an intense sound pulse that repeats over and over while the system remains active. This release occurs when the air inside the cylinder reaches very high values. As the piston reaches the top of its travel and under normal operation, that pressure is used to maintain the engine's continuous rotation. But when the engine brake intervenes, all that air is expelled in a matter of milliseconds, creating an extremely rapid release that gives rise to the characteristic acoustic shock. It is not a single burst, but a series of consecutive pulses generated by each cylinder participating in the process, and in a multi-cylinder engine, these pulses are repeated many times per second. This sound does not come solely from the compressed air released in the cylinders, but also from the way the truck's exhaust system channels and amplifies those pulses, since the manifold collects the pressure generated by multiple cylinders and directs it into the main pipes, which act as resonant chambers where the waves interact with each other. The shape, diameter, and length of the exhaust influence the volume and the final tone of the sound, and it is when all these waves combine that the deep, characteristic roar audible from the outside is produced. This same effect becomes more intense when the engine works harder, as occurs on long descents or when the vehicle carries heavy loads, because the cylinders must absorb more energy and the internal pressure increases, making the air release more violent and, therefore, louder. But that intensity is not the same in all trucks, because the sound of the engine brake depends on several factors related to the engine itself and the exhaust system, so that power influences the volume of each air release, and a larger engine produces stronger pulses, while the number of cylinders modifies the acoustic pattern, since the more that participate, the greater the number of pulses generated per second. The architecture of the exhaust system also affects this outcome, as it can amplify or soften the sound depending on its design, because a more restrictive or less muffled exhaust usually produces a more prominent tone, while configurations designed for urban environments tend to reduce noise, and those intended for heavy transport prioritize retention capacity even if the sound is more intense. For this reason, understanding why the engine brake sounds this way allows it to be related to the function it performs while the vehicle is in motion. The sound is not just an acoustic consequence, but a signal that the engine is absorbing energy to keep a mass descending under the force of gravity under control. That relationship between internal operation, mechanical retention, and vehicle control is what explains its real importance in safe driving. From there arises the central question: why is the engine brake fundamental to maintaining control and safety of the truck during long descents? On long descents, keeping speed under control does not depend solely on the friction of conventional brakes, because the engine brake allows part of the motion energy to be absorbed without generating the critical heat that would ultimately affect the main braking system, and that deep sound heard from outside is evidence that the engine is acting as an internal resistance capable of sustaining speed without the need to continuously apply the service brake. Mechanical retention thus becomes the main tool for maintaining control when gravity constantly pushes the vehicle downward. When the vehicle relies only on the service brake on a long slope, a known risk appears because constant friction raises the temperature of drums or discs beyond their operating limits, and as the heat accumulates, the friction material loses its properties. The system responds less effectively, and the braking distance increases so that the pressure applied no longer produces the same effect. The phenomenon known as fade appears progressively and can develop within a few minutes of continuous use. When this happens, the conventional system becomes unreliable. The engine brake prevents this scenario because it does not rely on contact surfaces or friction elements like pads or shoes, but generates retention from the engine's own compression cycle and the controlled release of compressed air, allowing constant internal braking for long periods without producing the extreme heat that would affect the main brakes. The engine absorbs part of the energy generated by the descent and dissipates the effort through its own cooling system, so that the service brake is reserved for specific interventions and not for sustained work that would exceed its capacity. This form of continuous retention also improves the truck's stability because it keeps speed within safe limits and prevents the vehicle from gaining momentum uncontrollably, allowing each curve and each slope segment to be approached at a regulated speed, which reduces stress on the transmission and avoids situations that could compromise vehicle control. The regularity of retention eliminates abrupt variations and keeps the truck in a state of continuous control. In many vehicles, this control does not depend solely on the engine brake, but is complemented by auxiliary systems such as hydraulic or electromagnetic retarders, which provide additional resistance and allow deceleration to be modulated without constantly relying on conventional brakes. The technical combination of these mechanisms creates a safe environment in which retention does not depend on a single element, and the result is a balanced system that distributes the load and prevents heat accumulation in sensitive components. This same balance also protects the service brake system because by receiving less work during descents, the conventional brakes remain in optimal condition for maneuvers that do require immediate intervention, so that in critical situations, such as avoiding a sudden obstacle or stopping the vehicle unexpectedly, the system responds effectively since it has not been exposed to prolonged use or high temperatures. In this context, understanding the relationship between mechanical retention, safety, and brake system protection allows the engine brake to be seen as an indispensable tool on routes with long slopes. Its function goes beyond providing additional braking, since it is part of the technical balance that ensures the truck maintains stability and that the main brakes are available when truly needed. However, its use does not depend solely on the mechanical needs of the vehicle. In many situations, the engine brake is subject to rules and restrictions that respond to external factors, especially related to the environment and the noise it produces during operation. From this arises a question that is not related to the mechanics of the system, but to the conditions in which it is used. What regulations govern the use of the engine brake, and in which situations is its activation limited for reasons that do not depend on the vehicle's operation? Although its technical function is essential on long descents, there are contexts in which its activation is regulated due to the level of noise it generates during operation, so that the mechanical safety of the truck must coexist with rules designed to reduce acoustic impact in inhabited areas. The characteristic sound of the engine brake is the main reason these limitations appear, because the sudden release of compressed air generates a sound level far higher than that of other vehicle systems and can easily propagate in populated areas, especially at night when any increase in noise is more noticeable. For this reason, many regions have adopted regulations that restrict its use in urban sections, not due to a mechanical problem, but because of the effect it produces on the area's sound environment. Where these rules are in effect, it is common to find specific signs indicating the prohibition of the engine brake placed at the entrance to towns, near residential areas, in zones with hospitals or schools, and on stretches where the noise could directly affect the population. Even with these limitations, the regulations do not intend to compromise vehicle safety, but rather to regulate the system's use in environments where acoustic impact is more sensitive, so that in areas where the engine brake is restricted, trucks can maintain control using other complementary resources such as retarders, downshifting, or progressive braking. These alternatives allow speed to be regulated when the slope is moderate and the risk of overheating conventional brakes is low, ensuring that the vehicle can travel without relying on the engine brake when regulations require it. However, when the route includes long slopes or mountain roads, the situation changes and regulations usually allow and even recommend the use of the engine brake, because under these conditions, safety becomes the main factor, and the characteristics of the road, the duration of the descent, and the vehicle's mass require a system capable of absorbing energy without degrading. From this same logic, the regulations do not contradict the technical necessity of the system, but establish reasonable limits in places where its sound effect could affect the population, so that in practice this set of rules allows the engine brake to fulfill its main role in critical areas while simultaneously avoiding unnecessary disturbance in areas where it is not essential. This combination of technique, safety, and regulation provides a complete view of the role the engine brake plays in the operation of a heavy vehicle. Seen from its internal operation, all this balance is explained because the engine can temporarily transform into a retention mechanism where air compression, early pressure release, and the internal resistance of the crankshaft make it possible to brake without generating the heat that would affect the service brakes. And this same principle also clarifies the origin of the deep sound that characterizes it, since it is the inevitable consequence of forcibly expelling compressed air in a repetitive cycle that acts as support on long descents. The role of the engine brake in safety is indisputable. It allows the truck to maintain stability on long slopes, prevents the conventional brakes from overheating, and preserves their responsiveness for specific maneuvers. At the same time, its acoustic impact has given rise to regulations that govern its use in urban areas, completing a vision in which operation, safety, and regulation are part of the same system designed to maintain control of heavy vehicles under any condition. With this complete picture, the question is resolved. It is understood why the engine brake is used, how it manages to brake without wearing out the main brakes, and why its characteristic sound is actually the signal that the system is performing its function. If you are interested in continuing to discover how other heavy transport mechanisms operate and why each is crucial for driving and safety, you can subscribe to avoid missing the upcoming videos. Each new piece of content continues exploring the real operation of trucks and the machines that move the world with the same clarity and detail as in this journey.